Okay, so good evening. My name is Devardhan Banerjee, and I'm a PhD PRF scholar from Indian Institute of Technology, Delhi. I'm going to start this session on course Waste to Energy Conversion. This is the live session number 3, and it's being conducted on 13 February 2024. We try to get some recap of the week's discussion on the particular NPTEL course. So in this week, the first lecture basically it covered the gasification. So basically it focused on the gasifiers, advanced gasification or plasma gasification process, comparison between incineration and gasification. These are the major parts which were covered. So if you see basically the slides, the particular first lecture of this week. So major types of gasifiers were discussed. Uh, Fixed bed, fluidized bed, entrained bed. This comes under the major types of the gasifiers, where basically the typical process conditions are from each other, and obviously the operating principle or operating mode is also different between each other. So, under the fixed bed, updraft and downdraft are two types of fixed bed gasifier. Bubbling fluidized bed, circulating fluidized bed, and double fluidized bed are fluidized bed reactor types, and plasma gasifier are also some other types. So the fixed bed gasifier, here the fresh feed is added to the top of the bed while air enters through the bottom. Basically it operates based on a counter current flow. So feed is added from the top and fresh air, oxygen or steam, whatever is the gasifying medium, is added from the bottom. Okay. Uh, contains about 25% water insoluble tars. That's basically obviously simple, one of the most simple gasification techniques, inexpensive process. The exit gas temperature is about 250 degrees Celsius, where the combustion zone operates at about a very high temperature of 1000 degrees Celsius. Its operation is quite satisfactory under a pressure condition, and it has its conversion and thermal efficiency. Okay. But also, like some other advantages is it's also suitable for dense high quality feedstock. So the difference between this is, you see, this is the updraft fixed bed gasifier, and the other one is the downdraft uh, fixed bed gasifier, where basically the air oxygen, this thing is provided at a particular way. So there is a concurrent flow fixed bed gasifier in this downdraft. Okay, so feed enters from the top and air from the sides, where in the updraft feed was entered from the top and the air oxygen this was entering from the bottom. So in the downdraft, the tar content in syngas is actually lesser than updraft. Both the pyrolysis products and oxygen free to react with the charcoal, and it's also a very useful technique for small scale applications in particularly. And this is the advantage, and also this is also the disadvantage because it limits its scalability. Okay. And also some requirement for the feedstock quality is there for this kind of gasifier. So it needs to have some low moisture and ash content or a high ash sintering temperatures. Fixed bed gasifier. There is fluidized bed gasifier. So bubbling fluidized bed, circulating fluidized bed, dual fluidized bed. These are the some of the examples. Okay. So the feed is fluidized in the gasifier. By the name, it is very much understandable. Certain heat transfer media is required. The syngas quality depending on the what type of fluidized bed you are using, and based on that, there is actually a feed property flexibility. Okay. Uh, Apart from fixed bed and fluidized bed, there is also the entrained bed gasifier, where basically the feed, air, oxygen, these all can enter from the top, and ultimately the product syngas can exit from the bottom. It can be used for large scale fine and dry feeds. Handling of low density feed in pressurized reactor is difficult, and its gasification temperature is actually quite high, about 1100 to 1400 degrees Celsius. Okay, and one of the newest kind of technique, the latest technique is uh, the plasma gasifier, where basically very high temperature, 7000 degrees Celsius, is actually obtained through plasma torch. So it's basically a localized temperature is created through the plasma torch instead of the normal conductive or convective heat transfer, normal like thermochemical process. Okay, the advantage is that the syngas qualities which we obtain from this kind of plasma gasifier is of very high quality. It's also wastes. So the feed quality is also actually like it can handle a different qualities of materials. The hazardous components broken down to elemental constituents, and the acid gases are readily neutralized. So obviously, when you're having a high quality of syngas as a product, so it can usually easily recover the fuel value of the waste. So the this efficiency, the waste to energy high at the plasma gasifier. However, the localized temperature or the energy consumption is a challenging thing, and also its scalability. There is an actually issue, and as I was saying, that's its heating value. If you see the output gas divided by electricity input is also a very considerably high 21.4. So we get a high calorific value syngas, which can be used as a fuel. So if you further see the plasma gasification mechanism, uh, so high voltage applied across the electrodes accelerates the free electrons. The energized electrons ultimately collide. So it's the formation of the plasma. How basically plasma forms, this mechanism is discussed here. You might also want to see that thing in detail. You can go back and check. So the formation of the plasma arc, and what happens is that there is a high voltage, there is a cathode and anode, create a voltage difference between the electrodes. It would basically accelerate or energize the free electrons. So these energized electrons, they will be collide, and they would get ionized or dissociate or excite the ambient molecules. So when there is an excitation, it means that there is a high energy production, and by the formation of this highly energized free electrons, there is a kind of spark is there, which propagates and which drives the reaction. So for creation of this kind of voltage difference, you need very strong plasma torch, which can have a power between 100 kilowatt to 200 megawatt. which can produce energy density up to 100 megawatt per meter cube. So the high energy electrons can work on all types of molecules and create radicals. Okay, what kind of radicals? Such as oxygen, hydroxyl, nitrogen, this kind of radicals, and indirectly H2O2, hydrogen peroxide, ozone, like this. These are basically like kind of byproduct. So all these radicals start chemical reactions to form final products. So basically radicals would be unstable. So at that highly energized condition, the low temperature condition, these radicals would react with each other or other molecules, other reactant molecules to form the final products. So there is a kind of the based on the feedstock properties, some the comparison are shown here between the fixed bed gasifier, fluidized bed gasifier, entrained bed gasifier, plasma gasifier. So you see that the for fixed bed, the typical particle size is quite high, about 50 to 150 millimeters, where slowly you go down. So basically, you need a good quality of feedstock. So the bubbling fluidized bed requires a lower, less than 50 to 150 millimeter particle size. For the CFD type fluidized bed, the particle size will be required less than 20. For entrained bed, it would be less than 1 millimeter, and for plasma, it is not very much important. So because of this entrained bed, there will very less particle size required. So keeping lowering the particle size, lowering the particle size below 1 millimeter is not an easy task. So you need some additional pre-treatment process like grinding, crushing, or there are different types of this kind of size reduction techniques. So this kind of size reduction pre-treatment techniques needs to be used for this kind of entrained bed technologies. Okay, and some of the examples where different industries which use uh, these different types of gasifiers are shown here. And as I said, that plasma gasification is the most advanced technique and the newest technique. So a typical process flow sheet actually shown. Basically, the waste storage from waste storage, the waste material will be fed into the main gasifier, where you get the fuel gas as output, which will be further cleaning. It can remove the HCl and sulfur, and you get the fuel gas. From that, from the gas turbine, you generate a steam, and also from the steam turbine. And after some further purification, multiple effect distillation, you can just separate out one the energy production. You take it for electricity generation, and the other part you can take it for distilled water generation. Some case studies, some examples are shown here. You can check those kind of uh, statements and products. Okay. So a basic comparison between gasification and combustion, if you see. So the gasification from the purpose point of view, gasification out for the generation of valuable gaseous products. Combustion is carried out for generation of heat. The major purpose is that. So gasification is basically a thermal and chemical conversion under a limited supply of oxygen. So it's basically a not exactly a complete pyrolysis. Pyrolysis is a part of gasification where complete absence of oxygen is there, but here you will not give a excess oxygen, so that to restrict it, combust it rather than need to get some valuable gaseous products. Okay, so that is why syngas is our main product from gasification. So, and also this, the usually gasification is carried out under a slightly higher pressure than the atmospheric. So the pressure requirement is also a bit higher than the conventional combustion technique. The solid products which we get is basically char or slag. Char is used as fuel. Char has also some other uses. We'll see that. Slag is basically used as a construction material. In combustion, you get the bottom and fly ashes and the solid product, which is used in the land filling or sold as a material for concrete manufacturing. Okay. So we see some of the sample questions. So fixed bed gasifier used for the gasification of coal and pet coke, and time of how many minutes? 15 to 30, 40 to 50, 50 to 60, 70 to 80. I know there also I'd like to say that there is some issue with this particular MS Teams meeting link. That is why there is slight uh, you know black window is coming for 1 second. Just bear with me. Uh, Maybe from the next day we can shift to some other link. I don't know. So fixed bed gasifier is one of the types of gasifier. It is used for gasification of coal and pet coke. So the retention time of fixed bed gasifier is of how much, typically how much minutes? 15 to 30, 40 to 50, 50 to 60, or 70 to 80. So the correct answer is 15 to 30 minutes. So for fixed bed reactor, the typical retention time is 15 to 30 minutes, whereas it's a quite high, actually the highest, one of the highest among the gasifiers. The retention time shown here is 10 to 100 seconds, but entrained bed is between 1 to 10 seconds, which is very less, very fast process. The pressure required for gasification of coal and pet coke in entrained bed gasifier is in the range of uh, the pressure range you have to answer 0.25 megapascal 0.1 to 0.85 megapascal, 2.94 to 3.43 megapascal, or 9.53 to 12.53 megapascal. So the correct answer is 2.94 to 3.43 megapascal. So in entrant bed, we carried out the gasification at a very quick rate and at a very highly elevated pressure and high temperature. So the pressure one of the highest among the different gasification techniques. It about 2.94 to 3.43 megapascal. That is the correct answer. The overall water gas shift reaction can be represented as there are these four options. CO plus H2O gives H2 plus CO2. So the delta H value you have to tell it's around minus 41.1, minus 14.1, minus 19.1 kilojoules per mole. So the correct answer is minus 41.1 kilojoule per mole. So the water gas shift reaction is a very important reaction in gasification technique itself. So here the CO plus H2O gives H2 plus CO2 is a reaction. It's typically an exothermic reaction where the delta H value is 1.1 kilojoule per mole. The lecture 2 and 3 in this week discussed on the syngas utilization. So discussed about the syngas utilization options, syngas cooling and conditioning, some important utilization techniques including methanol synthesis, Fischer-Tropsch synthesis, DME, dimethyl ether formation, other higher alcohol formation, synthetic natural gas formation, in production like that. And syngas cooling and conditioning, such as acid gas removal, different shift reactions, such as this water gas shift reaction, or just shown. Let us quickly see. So, syngas utilization options include the syngas to methanol and derivatives, which include the dimethyl ether, ethylene, propylene, polyolefin, oxochemicals, methyl acetate, acetic. So these kind of different derivatives can be formed from syngas. The Fischer-Tropsch liquids such as naphtha, waxes, diesel or jet fuel, gaseous fuels, those can be formed by the Fischer-Tropsch reaction. Synthetic natural gas, obviously it can also be used to generate steam and electricity, and syngas can be used to generate hydrogen. So syngas cooling and conditioning is one of the important part for it properly syngas to some valuable products. So it reduces the syngas temperature to extract, which is important to extract the valuable energy. It removes the chemical species which are actually not like very important for our valuable in the valuable product composition, which can actually be actually dangerous for the reactor or for the other parts, which can foul, corrode or erode system components or deactivate chemical processing agents and are environmentally unacceptable. Okay, so among the syngas cooling and conditioning process, acid gas processing, where you give the raw syngas as the feed in a hydrolysis reactor. Where basically the sulfides are converted as a hydrogen sulfide, and to remove the basically acid gas removal tank, and ultimately you get the clean syngas. And from that, the other part is the CO2, which can release it in the atmosphere or can utilize it in some other way around. The H2S we are also getting in the product stream. So this particular H2S gas can be enriched via the sulfur recovery, and that particular recovered sulfur can also further be reutilized to further in the sulfur processing technology. Okay. So acid gas removal technology. Some other important technologies are based on solvent absorption. So chemical absorption, we use some amines such as methyl diethanolamine (MDEA), some selexol, reddizole, this kind of different absorption, but these are basically physical absorption. So just based on some van der Waals force, physical forces, it absorbs mm, the acid gas, whereas the amines or maybe the newest new kind of technologies like the deep eutectic solvent or ionic liquid, they work based on the chemical absorption technologies. On the other hand, the warm syngas cleanup can be done by some other new technologies such as Eastman technology, RTI technology, like that. Okay. So basic syngas cooling and conditioning reactor is shown here, where you give the uh, bottom and the clean solvent from top to work as a counter current flow, and ultimately from bottom you get a dirty solvent taking up the dirty materials or impurities, and you get the sulfur free uh, carbon dioxide free clean syngas CO plus H2 from the top. Okay, so some comparison is also shown here, like the MDEA amine. It can actually remove 8 to 99%. The and the main important thing is that it works at the ambient temperature 30 to 35 degrees Celsius at a very low pressure, less than 2.94 megapascal. And some of the example companies are also shown here, like Union Carbide, UOP, Shell, Dow Chemical. They have basically using this for acidic removal. And it's the main advantages is basically its low capital cost, moderate operating temperature, only limited physical skill as in gas absorption takes place. So because of this strong chemical absorption, it is very much important. However, there are also some other physical absorption processes are also there, which you can also see, but they operate at a higher cost than overall system cost, including the sulfur recovery process and tail gas treating process could be more cost effective. Apart from that, uh, desulfurization technique in a adsorber, and after that some regeneration technique, some close process, direct sulfur recovery process, these kind of high temperature processes which can directly use clean the water from the gasifier. These are also there, obviously based on some chemical reaction. So in the earlier case, what you have to do, you have to first cool down your warm syngas which you are getting from the gasifier. But in this kind of case, you can actually use the warm gas into a desulfurization technique to remove the sulfur from the syngas and get the clean syngas. One such example is the Claus process, where basically the H2S O2 gives us SO2 plus H2. So you see the overall technique. It works on mixed alumina iron oxide mixed catalyst, giving the elemental sulfur as the product and H2O in this particular mixture as the product. Okay. Uh, Among these, in this particular syngas cleaning options, water gas shift reaction, as discussed earlier, important reactions where the main reaction is the CO plus H2O gives H2 plus CO2. The types of water gas shift reaction are basically, it can be of many types, like based on the operating temperature. It can be of high temperature shift reaction, where a iron chromium based catalyst used at a higher temperature to carry out this reaction, 320 to 450 degrees Celsius. A low temperature at around 200 to 250 degrees Celsius on a copper zinc alumina catalyst. Also, it can be also subdivided based on its position in the flow sheet. So if it takes place after the acid gas removal, so it is called as a sweet shift reaction. Whereas if it takes place after before the sour shift, before the acid gas removal, it is called reaction. Okay. Some of the further, compositional conditioning characteristics of this particular sweet shift and sour shift reactions are shown here uh, for this water rate shift reaction, and ultimately the typical composition, how we'll actually get the syngas composition. Basically before reaction, if you see the hydrogen percentage is actually increased from 43 to 61 percentage. The CO percentage is actually decreased from 49 to 1 percentage. CO2 is increased from 4 to 35 percentage, like that. And if you see some comparison, so from the catalyst point of view, the switch shift is usually more expensive than the sour shift, whereas the size of catalyst bed in the reactor for the switch shift reaction is actually smaller, whereas the catalyst bed required in the sour shift is actually higher, which means that the amount of the catalyst required, it might be lesser in switch shift than the sour shift, but the catalyst required is much more expensive in the switch shift. So there is a trade-off kind of thing. One thing is good, another thing is bad. So you have to optimize that thing based on the uh, conditions and the output which you are getting. Okay. Apart from that, Fischer-Tropsch synthesis is one of the also important techniques which for utilization of the syngas. So the syngas is converted to wax, naphtha, and diesel in this particular Fischer-Tropsch synthesis, which are followed by upgradation. The wax is hydrocracked other products, and in this particular Fischer-Tropsch reaction, there are multiple reactions occur. Okay, so there are multiple reactions occur. Among them, some reactions are shown here. Overall, the paraffins and olefins and also the water shift reaction is also one of the important part of the Fischer-Tropsch synthesis. Overall, the reaction is strongly exothermic. The delta H value of minus 180 kilojoule per mole. And the overall process of the Fischer-Tropsch reactor, where you get the light wax, the diesel, naphtha, kerosene as the output. So the further what we are getting for the Fischer-Tropsch reactor, we would want to do the hydrogenation. Okay, so we'd want to do the hydrogenation reaction for the product of the Fischer-Tropsch reactor, and after that, for further after further distillation, we get the off gas, and we ultimately get the kerosene distillate, Fischer-Tropsch diesel, or it can get some combustible product also. Okay, some typical process conditions and catalysts are shown here. The pressure temperature requirement, the GHSB, and some iron based, cobalt based catalysts which are important in the Fischer-Tropsch reaction is also shown here. Okay. And apart from that, some commercial data are also important. After the Fischer-Tropsch methanol synthesis can also be done. Methanol is actually being promoted as one of the possible transportation fuel. So from biomass or waste, we get the syngas by gasification and then can use the syngas to form the methanol using metal catalyst. Typical catalyst reaction is shown here, which is CO plus 2H2 gives the methanol. So two important processes for methanol production from syngas are patented by ICI and Lurgi, first commercialized in 1970. It currently accounts for more than 70% of the undergoing projects. Methanol synthesis from carbon oxide and hydrogen is usually achieved over copper and zinc oxide catalysts according to the following main reaction. CO plus 2H2 gives methanol. CO2 plus H2 gives CO plus H2O. CO2 plus 3H2 gives methanol and H2O. There are multiple this kind of reaction which can occur on the methanol formation. The methanol synthesis is an exothermic reaction and is favored at high temperature and high pressure and low temperature. Uh, so basically this H2 minus CO2 and CO plus CO2, this ratio is called as the R value, and this particular R value is important, which will determine how much syngas feed we require. The typical process operating temperature is about 220 to 250 to 80 bar pressure, and it uses a series of catalytic adiabatic reactor beds. Some other undesirable or maybe desirable for other purposes. These reactions are shown here, like dimethyl ether formation, some hydrocarbon formation, or ethanol formation. So for this, some other reaction, other catalysts are also there, like chromium zinc based catalyst, zirconium potassium based catalyst, zirconium manganese potassium, like that. Okay. So the next question is, the liquid products formed from syngas in Fischer-Tropsch synthesis is wax, naphtha, diesel, or all of the above. We have discussed this thing. So as discussed, the correct answer is all of the above. Basically, by Fischer-Tropsch synthesis, we get all of these products: naphtha, waxes, diesel. Uh, so all of the above is the correct answer for this question, as liquid products formation from syngas via the Fischer-Tropsch synthesis. So the overall Fischer-Tropsch synthesis reaction is, to solve the puzzle, is whether it's exothermic or endothermic, and what would be its enthalpy of reaction. The correct answer is it's strongly exothermic reaction and its enthalpy is minus 180 kilojoule per mole. The overall Fischer-Tropsch synthesis reaction thus is strongly exothermic and the enthalpy of reaction is minus 180 kilojoule per mole. Methanol synthesis from carbon oxides and hydrogen is usually achieved over which catalysts? Zinc and aluminum oxide, copper and zinc oxides, or none of the above. For methanol synthesis from the syngas, what catalysts are used? Zinc and aluminum oxide, copper and zinc oxides, nickel and iron oxides, or none of the above. So the correct answer is copper and zinc oxides. So for methanol formation, the typical commercial catalyst available from syngas is the copper zinc oxide over alumina. So this kind of ternary catalyst is important to selectively form from the syngas. Okay, so this particular reaction is also like it's shown here in detail. For homogeneous phase reaction, there are two processes have been proposed: the BNL method and the methyl formate formation method, where basically a homogeneous nickel catalyst or a mixture of copper-based oxide and alkoxide catalyst. This kind of catalyst are the whereas the basically the reactor selection, if you see, it can be carried out if in is a gas liquid combined phase. So the bubble column reactor or gas lift reactor. So this kind of different reactor selection is also there in the entirely like solid liquid phase. It can be carried out as a start tank reactor. Liquid liquid phase it can be carried out in the column reactor or start tank reactor. There are these kind of multiple opportunities are there for this part, you know, technique to form methanol from syngas. Okay, and in further conventional methanol technology, where conventionally a multi-tubular packed bed reactor with recycled steam is employed for the methanol synthesis. There's some challenges such as the catalyst deactivation via thermal sintering of catalyst at the high temperature because you're using copper as a catalyst. So at above 300 degrees Celsius to crystallize, which reduces the activity of the catalyst. These are the things you want to see. You should go back and check the PPT slides. Okay. So some basic reaction mechanism is also shown here uh, for the methanol synthesis, where basically details of the role of the copper phase and the role of the zinc oxide. This kind of catalyst role is also shown here. Further, after the methanol synthesis, the dynamics is also shown here. So apart from methanol, like from methanol, so by using an acid catalyst, the methanol can be further converted to DME, or from syngas, if you're using a bifunctional catalyst, it can directly produce the DME. If you use a H2CO ratio 1, so it can directly produce a DME using. If you're using H2CO ratio of 2 is to 1, it preferentially try to go to the methanol formation. There is a metal catalyst or suitable catalyst is present. Okay. Further details of the DMA synthesis also shown here. What kind of catalyst is required? So use dehydration catalyst such as alumina with copper zinc, already told. This kind of catalyst is also important. Some basic commercial plan details also shown here, which are discussed in this particular lectures. Okay, I'm not going into much detail of this kind of basic theoretical things. So these are basically facts, and you can check and you should study, because any of the this kind of statement based things might be important for your examination, this particular course examination point of view also. So if you see the next particular on the pyrolysis, the next lectures, it covers the contents of the definition of pyrolysis, its mechanism, the types of pyrolysis, its the operating conditions, uh, and end product distribution, use of pyrolysis products, properties of bio-oil, because when you're using biomass as the source of the pyrolysis, the feed of the pyrolysis, typically you're trying to make the bio-oil as a target product. The properties of bio-oil product, and the raw bio-oil, it cannot be used as a fuel or other purposes. So the need for its upgradation, the catalytic pyrolysis, the use of catalyst, pyrolysis reactors, and finally the utilization of pyrolysis char and gases. Okay, so pyrolysis composition of the carbonaceous material by the heat in absence of oxygen. Okay, so if you give biomass or some other waste, heat it in absence of oxygen in an inert atmosphere, it would preferentially would form some solid product which is known as a char, some liquid product known as a bio oil if the biomass is the feed, some gaseous product with composition of CO, CO2, methane, hydrogen, some H2O. So pyrolysis is the first step of gasification and combustion process. It is the only thermochemical process which converts different types of biomass and organic waste into solid, liquid, and gaseous fuel. If you see the basic mechanism, it contains multiple phases. So in the primary phase, there is a decomposition reaction happening, which lasts about less than 1 second. The primarily at about 450 to 550 degrees Celsius, the bio decomposed into gaseous products and some solid product and some other volatiles. In the second phase, the cracking and condensation occurs. The volatiles get further cracked, and it produces the bio oil and some other gaseous components. Okay, so under atmospheric conditions, this bio oil can get recrystallized or repolymerized to form some char from solidified form, or some gaseous product. So the factors which are important in this particular method are the operating temperature, heating rate, residence time, feed size, like that. Basic systematic flow diagram of a semi-batch pyrolysis reactor is shown here. Uh, the temperature is about 400 degrees Celsius. Uh, the residence time is about zero point 0.1 second, and pressure is about 75 kilopascal. Okay. So different types of pyrolysis technologies, such as if you give the heating rate as a very low, very slow, so ionization technologies. So it is used basically to form the charcoal or the char as the major target product. It takes about the residence time is about from hours to days. If you slightly increase the heating rate, but not too much, and slightly increase the operating temperature about 400 to 600 degrees Celsius with a medium heating rate and residence time about 5 to 30 minutes, you'll get basically the biochar and gases as major product. And if you increase the residence time in an intermediate temperature with a low heating rate, again a slow heating rate, you'll get a varieties of charcoal, liquid and gaseous products. Whereas if you go for a fast pyrolysis technique with a very fast heating, like only uh, residence time of about only zero point 0.5 to 5 seconds as shown here at a high 50 or maybe even higher with 750 also, the very high faster rate, you'll get majorly the liquids and gaseous products, not enough solid no, charred products. The flash pyrolysis is about further increasing the heating rate, lowering the residence time. So if you lower the residence time to maybe less than 2 seconds, you will get again the liquid. If you lower it below 1 second, there will be also some variation in the product stream composition. And apart from that, the newest techniques such as under vacuum conditions, vacuum pyrolysis, and some in some water conditions of hydrolysis or methanopyrolysis. These kind of technologies are also gaining much importance. Search for these particular technologies and read about them. So as I was telling that if you increase the particular temperature as one of the important parameters, to increase the temperature, basically the biochar formations, the biochar yield is gradually decreased. The oil formation initially increases and then after a certain temperature it further gets decreased with and monotonous increase gaseous products with the with respect to the operating temperature. Okay. A basic flow sheet from continuous from operation of pyrolysis is shown here. The basic the pyrolyzer and then there is a separator. The char is separated and then it can again feed back to the pyrolyzer to give the energy for the pyrolysis, and then we want to condense our condensable liquids in a condenser to and some water which can be further purified and can be used. Okay. Um, the pyrolysis products can be used in various applications from chemicals, transportation fuels, heat and electricity generation. So this kind of different applications are there based on the composition of the products you are getting from the pyrolysis. Okay, chemicals you can get resins, fertilizer, different flavors, adhesive, acetic acid, this kind of chemicals we can obtain from the pyrolysis bio oil. And among fuels, the upgraded bio oil, which is on the HDO. HDO is the process of uh, upgradation, industrial upgradation process of bio oil. Hydrodeoxygenation technique, where basically we hydrogenate over a catalyst particles, our bio oil. Okay, so some properties of the pyrolysis bio oil and their reasons. You can check this kind of uh, and if you want to use the bio oil as a substitute of our conventional, transportation fuels such as diesel, you see the bio oil have a higher oxygen content, higher water content, lower pH, and low heating value on the calorific value, a highly viscous nature, high ash content. So these are the drawbacks of the conventional, you know, and for that reason, the bio oil needs to be upgraded. Uh, that is the thing. However, despite of these problems, the carbon neutrality, the utilization of the waste biomass for the production, its storability and transportability as a liquid fuel, its high energy density when we try to compare with the biomass gasification fuel, its possibility to utilize it in the power generation system, uh, and also the large power stations. This kind of advantages make what bio oil as an potential alternative in the future of the transportation field. Also, some disadvantages are there, which already I told. The high oxygen content, it results in low energy density, and also due to the high oxygen content, bio oil is typically very much unstable in nature. Okay. Uh, it has a typically a lower calorific value. It can swell and soften the natural or synthetic rubbers and corrode the metal components because of its the acidic things it has, acids and some other acids as its component. That is why it has a lower pH. Mm. However, the current engines and reactors, all those things are needs to be a bit modified to be directly using bio oil as our uh, transportation fuel, and also obviously we need to some technical requirement for converting the liquid bio oil. So this is a kind of an emerging field. Okay, this particular bio oil upgradation technologies. So a lot of research work is actually going on for this particular bio oil upgradation technologies. So some physical and chemical methods are there, like filtration, emulsification, solvent addition. These are the some uh, hydrogenation, basically using a catalyst, catalytic vapor cracking, reaction with alcohols. These are the some chemical methods which are used to lower the oxygen by carbon ratio, higher and the basically the calorific value, to remove the oxygenated components, which are actually responsible for reducing the quality of the bio. That is why the hydrotreating or hydrodeoxygenation kind of thing are actually done. Okay. So the question is, dash is a thermochemical process which converts different types of biomass and organic wastes by the application of heat in incineration, drying, pyrolysis, or all of the above. So as discussed, pyrolysis is the correct answer. So pyrolysis is such a thermal decomposition technique which is carried out to convert different types of biomass and waste by application of heat in the absence of oxygen. Pyrolysis is the only thermochemical process which converts the different types of biomass and organic wastes into fuel, gaseous fuel, or all of the above. Correct answer is all of the above. Basically, as discussed, it can form the char, as the bio oil as the liquid product, and the gaseous products in the formation, combination of CO, CO2, H2. So it can form all of the products. So coming to our discussion, the catalytic pyrolysis uh, is an important technique which is operated at atmospheric pressure using a wide variety of catalysts which are available based on the product needed and can be integrated in the unit used for pyrolysis. Some catalysts are like zeolites, SBA15, ZSM5. This kind of zeolites are important for this particular catalytic pyrolysis. Okay. The reactors, if we talk about for the pyrolysis, fixed bed reactor, fluidized bed reactor, circulating fluidized bed reactor, ablative reactor, rotating cone reactor, vacuum pyrolysis reactor, and Auger reactor. These are some important pyrolysis reactor types which are used in this particular technique. Fixed bed reactor has these usual advantages like simple design, uh, independent of whatever kind of biomass size or waste material particle size you are giving. Right? However, the bio-oil yield from the fixed bed reactor is typically very low, about 35 to 50%. Also, it has a long residence time, uh, a high carbon conservation, uh, low ash carryover, and also it's very difficult from a fixed bed reactor to remove the char. because it tends to get deposited. On the other hand, fluidized bed reactor has advantages such as high heat transfer rate, uh, facile heat supply to the fluidizing gas, the limited charge abrasion, which was one of the disadvantages in the fixed bed reactor, certain particle size limit, which is less than 2 millimeters, and also it also has a simple reactor configuration and controlled, residence time of solids and vapor, which can be actually tuned or controlled while the fluidizing gas. Okay, and you can see the fluidized bed reactor has a quite high bio-oil yield, about 70 to 75 percentages. In fluidized bed, it also has this kind of certain features like a high heat transfer rate, high char abrasion from biomass and char erosion leading to high char in product. The particle size limitation is also there. It can entertain up to a highest particle size of 6 millimeters. However, it's considered as a relatively complex system, and also the solid recycle is required in this type of reactor. Okay, uh, and you can see the bio-oil yield is actually also high. Like the fluidized bed reactor is about 70 to 75 percentage, and it's a well understood technologies. And if you see the modes of heat transfer, it's about 80% the heat transfer occurs via the conduction technique, 19% via the convection, and only 1% via the radiation technique. And another advantage is that the base variation in the heat transfer technique, it has a good thermal control. Okay, and it can entertain a large chunks of particles also. However, it should not be uh, greater than 6 millimeter, a typical particle size. Okay. Apart from that, there is ablative reactor, which also accepts a large size feedstock. Uh, it it has a compact design, very high mechanical charge. However, it has a heat supply problem. So based on that, the reactor is actually typically a bit more costly, and the reaction rate is also slower in the ablative reactor. And the heat modes of heat transfer, if you see, the majority is made by the conduction technique. That kind of variation is not there. Almost all of the heat transfer takes place via the conduction. Only 4% by convection and 1 radiation. The rotating cone reactor, it its advantages are based on the centrifugal force moves the heated sand and the biomass. Okay, based on the centrifugal force which is being generated by the rotation, these actually uh, carries out the reaction. The no and the is actually required in this particular reaction. So it's kind of considered as a much complex process, and because it needs to pass through this particular kind of cone, so a smaller particle size is required. However, these kind of technologies are not proven at the commercial scale, are actually kind of evolving technologies. One such process is the vacuum pyrolysis reactor. If you see the bio-oil yield when the vacuum pyrolysis reactor is used, is only 35 to 50 percentage. Advantages of producing a clean oil. Okay. However, solid residence time is actually quite high. Due to that, what happens is the reaction rate is very slow, uh, and it requires a large scale equipment, and the heat and mass transfer rate is actually slower. Because of that, the overall reaction rate. Also, some other like Auger or screw type of reactors is also there, where also the no kind of carrier gas is important, and it can be carried out at a lower operating temperature. Similar to the plasma gasification technique, there is also plasma pyrolysis technique, where it has again the trade-offs like high energy density, high heat transfer, high temperature, and very good control, reaction control is there as the advantage pyrolysis reactor. Whereas I already told that high electric power consumption, high operating cost, and the requirement of fine particles are some of the disadvantages or the challenges this particular evolving technique of plasma reactors. Some of the comparison based on different aspects are shown here between the different parallel. You can go back and check these data, and some commercial technologies, commercial organization which are using different types of technologies for the bio-oil production. Okay, so bio-oil production is a commercialized process. So apart from the bio-oil, there is also a solid production is there via the pyrolysis, which is called as a char. Biochar can be used solid fuel, soil conditioner or fertilizer, activated carbon production, adsorbent. So it has a multiple and you know utilization purpose. So you might not think that bio oil is only the important thing and the other parts are not so important. It's not like that. Pyrolysis is a very useful technique where the solid, liquid, gas, all types of products are very useful. Okay, so the biochar activated carbon. This is also another type of study, and the carbon, the modified carbon production from the pyrolysis char. Okay, it can be produced via the chemical or physical activation by the use of an impregnating agent using a acid base, or maybe as a physical activation which burns off the the skin tar, and which actually from the pore skeleton which are formed during the carbonization. Apart from solid and liquid, the gaseous products, as I told, the nothing is actually waste. So the gaseous products are also important. It mainly contains the CO2, CO, methane, and hydrogen, which has a gross calorific value of 6.4 to 9.8 megajoule per kg. So it can be used to provide the process heat for pyrolysis. It can go basically to by the recycled gas can actually provide the process heat for the pyrolysis. Carbon monoxide and hydrogen, if you have the syngas. Syngas is itself is also of gaseous fuel, or also it can further be converted into some other valuable products, some liquid fuels via Fischer-Tropsch synthesis, like that. Uh, if you have hydrogen, hydrogen is itself considered as a very nowadays. Uh, if you see the hydrogen powered car, hydrogen powered transportation vehicles are actually getting much and much popular. So that is one of the use. Apart from that, that particular hydrogen can be used to upgrade the bio oil. As already told, that bio oil have a high oxygen content, low calorific value. So we need to hydrogenize. We need to hydrotreat it. So this particular hydrogen can be used in the hydrogenation which we are already getting from the pyrolysis reaction. So nothing is getting wasted and everything is getting utilized. So last couple of questions for today. The identify this type of pyrolysis reactor in presented in the schematic diagram. You see shown the particular different types of the pyrolysis reactors earlier. So if you see, this is basically a circular with CFB type pyrolysis reactor. Okay, as already I discussed its advantages and disadvantages of some of these kind of aspects. You can go back and study in further detail, which was taught in the last week's lecture. And the last question for today is biochar produced in the biomass and waste can be used as solid fuels, solid conditioner or fertilizer, adsorbent, or all of the above. So as discussed, biochar is actually of a multiple uses material. It can be fuel. It has a considerable calorific value. It can be used as a soil fertilizer or soil conditioner to upgrade the soil quality for crops production and all. It can be converted for activated carbon formation or some other forms of carbon, graphene, carbon nanotube, graphene oxide, this kind of carbon based products, carbon based materials be used, and it can be used as an adsorbent. Biochar has also some good pore characteristics, absorption characteristics, so it can be used as an adsorbent. So all of the above will be the correct answer. So with this, uh, I stop my presentations and thank you all for joining today. So if anyone has anything to discuss, then discuss. Otherwise, we'll end the meeting. Okay. So thank you for joining. Uh, we'll disperse now. Thank you.